Okay, 102 students, I thought I'd try a solution here. I got a couple questions on this one. So from chapter 11, number 8, and I think probably the main reason I got this question is there's a little bit of a background chemistry that is kind of implied in this problem, and I suspect not all of you have had that chemistry background. See, it starts off, it says, given that a nitrogen molecule has a mass of 28 AMU. So I'm just going to write down 28 AMUs. Now, I'm glad they just give it to you. But if you know a little bit of chemistry, but not a lot of chemistry, this might bother you. Because if you look up in a periodic table and you look up nitrogen, you'll see the number 14 on the atomic mass. Now remember, we said here that those black numbers on the periodic table, what we call the atomic mass, have four meanings. The first one would tell us the number of nucleons. So this would say that we have 7 protons and 7 neutrons. I'll just say N for neutrons. Okay, so that's the first thing, because again, the 14 would tell us how many nucleons we have, which is the total number of protons and neutrons. And if we look at the periodic table, we see its atomic number is 7. So we know there's 7 protons, so there must also then be 7 neutrons to make the total 14. So that's one of the meanings. The other thing is that you would say that one individual atom is 14 atomic mass units, or another interpretation of that 14 is to say that you would get 14 grams if you had 1 mole of these nitrogen atoms. Now, I don't know if you caught that, but I keep saying atom here because there's a little kind of subtlety here with this problem. And again, this is why they say 28, that you may or may not know. But as you look on the periodic table, nitrogen is in the 5th column. Maybe if I do a rough drawing of a periodic table, we've got hydrogen here in the first row, and then the second row comes across, and maybe looks something like, went too high, sorry. Really messed up my drawing there. But what I wanted to see here is in this second row here, let's see, we would have hydrogen. This must be one over here, helium. So this must be lithium and beryllium, boron, carbon, and then finally nitrogen. And that's the real key. The nitrogen is what we call the 5th column. So not counting this middle area, which is often referred to as the d orbitals. But it's the 5th one over, which also means it's 3 away. And if you, again, know a little bit of chemistry, and you don't have to know completely this, but that means nitrogen wants to form 3 bonds. What it really means is in the second shell, there are 5 electrons. And if I do kind of a Lewis electron drawing here, this electron on the nitrogen wants to bond, this one wants to bond, and this one wants to bond. And they love to bond with themselves. This is called covalent bonding. And most of the things in the world love to bond to themselves. It's just these noble gases, and hence that's where the name comes from, because they don't want to mix with all the other stuff. They're, you know, the old days where you have nobles and then the commoners, and the nobles didn't mix with the commoners. Well, nitrogen is one of these commoners, and it loves to mix with itself and other things. And if you put then nitrogen and maybe make this bond coming out with another nitrogen, with its bond coming out, boy, they just love to hook together. And then the one going up, it's actually very three-dimensional. It goes up and down. It likes to curl over and form what's called a pi bond. And so it looks something like this. And so you've got I'll call the better connection right there, called a sigma bond. And then it arcs over and makes a second bond. That's a pi bond. And if you can imagine it doing that same thing in 3 dimensions, so it would curl up here. We like to do nitrogen 1, 2, 3, has 3 bonds connecting it to another nitrogen. So this is called a nitrogen molecule. And that's my point here. Do not confuse nitrogen atom with nitrogen molecule. And this problem is very clear. It says, given the nitrogen molecule, so there's 2 of them. So 14 plus 14 is 28. All right. So, like I said, if you know nothing about chemistry, you probably just accepted the 28 and moved on. If you know a lot about chemistry, you said, okay, well, 28 makes sense because we're going to have this triple bond and the nitrogen is going to hook together and it's going to make then a molecule, which is 28. If you know a little bit about chemistry, you might go, oh, now wait. I thought nitrogen was, 14. That's what it says on the periodic table. So, anyways, if anybody's having troubles with that, and it sounds like a couple of you are because I got, some comments about I don't know how to do the problem, but B, I don't even like the numbers. I don't like the number 28. So I thought I would begin by saying it's 28, okay? They say it's 28, accept it as 28. Let's just move forward with the problem. And if you don't know anything about chemistry, and this book is kind of assuming you don't know really anything about chemistry, but I thought I would expand and say, look, this is the chemistry part of it, okay? And that's why they say it's a 28, because that was, kind of one of the questions I got. Somebody was just looking at this going, whoa, I don't get the 28. And I thought it was 14. And so as a atom, it's 14. As a molecule, it's 28. All right, so that's why we often write it as N2. You might be more familiar with O2 or H2. These are all what we call diatomic molecules. And so they float around in the air and they hook to each other. Okay, a covalent bond. All right, so knowing then that the atomic mass number is 28, which again we can interpret as 3 ways. Let's just do the approach that they say. They say that it has an atomic mass of 28 AMUs. But what that also means is that I have 28 grams to make up 1 mole. And a mole is 6.02 times 10 to the 23rd. Particles or pieces, in this case, molecules. So if I had 28 grams, now I don't have that much, but if I did have 28 grams, I would have 1 mole. So this problem then is asking you to think a little bit about that. It would be like, if my analogy I like to do, because for some reason the word mole and Avogadro's number and it being so big really confuses students. Think of it as something different. A dozen is a good example. So if I said, instead of a dozen, I said a half a dozen, I think you'd be able to figure that out. You would go, well, you have 1/2 a dozen. And so you would go 1/2 times 12, right? Or if I said a quarter of a dozen. Now, the reason I bring that up is instead of a dozen, I have a mole, okay, 6.02 times 10 to the 23rd, okay. But that's if I had a whole mole or a whole dozen. I don't. Do I have a half a dozen or a half a mole? Well, no, because I need a full 28 grams to make a mole. So I guess a half a mole would be 14 grams. I don't have that. Well, what do I have? I have 1 gram. Okay. So I would say that I have 1/28 of a mole. It would be like saying if I had 1 cookie, I have 1/12 of a dozen cookies. I only have 1 cookie. So I have 1 out of 28. I have 1 out of 28 of Avogadro's number. And that's my thinking on how to do this problem. Okay, so I will take 1 and divide it by 28, and then take that number and go 6.02 times 10 to the 23rd, and come up with 2.15 times 10 to the 22 molecules. So that's how many molecules I would need to make 1 gram of this nitrogen molecule, N2. Okay, hope that helped.